Good day, students. Now we talk about a biopotential and about electric dipole and the physical basis of electrocardiography. But first of all, I want to talk about laboratory work, especially for students who study online. You have to read and calculate and design 5 reports of laboratory work. And first, our laboratory title Reversible Pendulum. It's a laboratory work number 5. You have to read a topic of this laboratory work on this topic, and experimental data done you and read and watch a video, read topic and watch video for laboratory work number 5. Look at these test questions after laboratory work. It's an end in topic. And you have to choose a laboratory work number 5 report, print it and fill the gaps. Work title, reversible pendulum, date, name of student, the purpose of work, equipment and materials, and experimental part. You see this all data was done for you, and you have to calculation average value of T1 and average value of T2. The first knife edge, it's first experimental data. The second knife edge is a second experiment, and you have to calculate average value and use this formula. Calculate average time. The first knife edge and the second knife edge and this formula, and write down your result in a second. Then you have to calculate a period of 10 oscillation and use this formula, and you have to calculate the period in a second and write down in the table the value of period here, period 1 and period 2. And then you have to calculate the average period in a second and calculate free fall acceleration. And use this formula to calculate our first free fall acceleration for use a first period and use a second period and the average. In the end of the work, you have to write down in conclusion and compare your experimental data with theoretical and write down about it. And that's all. Please do this laboratory work and send me your report. But now, our lecture about biopotential. And we talk about a mechanism of substance transport across the membrane. The mechanism or kinds of substance transport can be classified into two groups. And first group, it's a passive transport of substances. It's named so because it does not demand cell energy input for transport of substances across the membrane. The mechanism of passive transport includes different kinds of diffusion: ordinary diffusion, facilitated diffusion, electrode diffusion, osmosis, filtration. And the second, active transport of substances. This kind of transport involves cell energy input. Look at this picture. Passive transport. Passive transport through the membranes is related to some kind of diffusion. In the simplest understanding, diffusion is transfer of substance from a space with a higher concentration of the substance to one with its lesser concentration. Ordinary diffusion of uncharged particles is described by Fick equation. At ordinary diffusion, the direction of a substance transfer is opposite to that of the substance concentration gradient. If the substance concentration in space depends only on one coordinate, for example, on coordinate x, then the first Fick equation is here. Look at this equation, where dm divided by dt is a rate of diffusion, mass of the substances borne in a unit of time through the area S. dc divided by dx, a gradient of concentration x, distance between points in which concentration are observed. D, diffusion coefficient, which depends by substance nature, densities and viscosity of medium, temperature and other factors, and is measured in centimeters in square by second. If one introduced the notations, phi is the substance flow, more exactly the substance mass flow, and g is the substance flow density. The first Fick's equation can be written in the form. Look at here. Direct diffusion across the phospholipid bilayer. The number of substances which are capable of diffusion directly across the phospholipid bilayer is very limited. These are some gases, for example, oxygen and carbon dioxide, and non-electrolytes which are soluble in lipids. Most substances that are transported across the membrane cannot diffuse across the phospholipid bilayer. Diffusion through pores. Diffusion of most substances across the membrane is affected through specialized membrane formation known as pores or channels. They are formed from integral patterns. Diffusion of water, some sample organic compounds, and iron occurs through the pores. It's typical for porous diffusion that the membrane permeability for a given molecule or ion depends on the channel and the molecule dimensions. For ions, transport also depends on the ion charge and the potential difference between the membrane sides. Facilitated diffusion. Facilitated diffusion is an effect by means of so-called potential carriers. At facilitated diffusion, the molecules of the transported substance from a complex compound with the molecules carriers. Facilitated diffusion is characterized by the following. Permeability of membrane, a stream of substance phi is significantly higher than diffusion of phi determined by the law. Second, saturation, a stream of substance phi increase only up to achievement of some limited value of gradient of concentration. Third, high specificity. The certain substance carried only with a similar structure. And fourth, the expressed sensitivity to low concentration of inhibitors and activators of a carrier. Fifth, integrity with streams of ions through a membrane. Electrode diffusion is diffusion of charge. Look at this picture. Electrode diffusion is a diffusion of charged particles, namely ions. The phenomena of electrode diffusion involves not only availability of ions concentration gradient in the medium, but also the presence of an electric field potential gradient. The electrode diffusion phenomenon is described by the Nernst-Planck's equation. And look here into this equation, where U is the ion mobility, Z is the ion charge expressed by elementary charges, F is a Faraday constant, and phi is the electric field potential, and d phi by dx is a potential gradients modulus. Taking into account that ion mobility is equal to d divided by RT, where R is a universal gas constant and T is the absolute temperature. The Nernst-Planck's equation can be rewritten as this form. Osmosis is a locomotion of a dissolvent in biological object water from range with a smaller concentration of solute in a range with a greater concentration. As a matter of fact, it's a diffusion of a dissolvent. This appearance is observed in the presence of semi-permeable membranes between a specified area. Electroosmosis is a locomotion of a dissolvent in an electrical field if molecules of dissolvent are charged, or owing to the osmosis accompanying locomotion is a dissolved charged particles. Abnormal osmosis happens at presence both of concentration gradient and condition for electroosmosis. If the electrical gradient interferes with osmosis and locomotion of dissolvent goes on an electrical gradient against concentration gradient, negative abnormal osmosis is observed. If electrical gradient only reduces rate of transmission on a concentration gradient or even enlarges its peak about a positive abnormal osmosis. Filtration is a movement of water and solute molecules across the cell's membrane due to hydrostatic pressure generated by the cardiovascular system. Depending on the size of the membrane pores, and only solutes of a certain size may pass through it. Active transport. Active transport of substances across the membrane is related to the action of ion channels. The channels are formed by integral membrane potential whose hydrophilic polar groups are directed inward the channel. Most channels have intrinsic selectivity, which the capacity to let only certain ions pass. Sodium, potassium, calcium, and chlorine channels are unknown. Ion channel action is regulated by the cell due to conformational alteration of the potentials, which form the walls of the channel. It can switch from the open state to the closed one and vice versa. One of the causes of such change, for example, is the membrane electric field change. And look at this picture. Active transport of substances, unlike passive transport, is related to the transfer of substances across membrane in the concentration gradient direction from the field where the substance concentration is less to the field where it is higher. Such transfer is impossible without cell energy input. Active transport of substances is often related to the action of so-called ion pumps. The sodium-potassium pump of plasma membrane, the calcium pump of sarcoplasmic reticulum membrane, and the proton pump of mitochondria and chloroplasts. Active transport includes transfer of different substances, for example, sugars, across the membrane of intestine epithelium cells. We will consider the sodium-potassium pump. 3 sodium ions and 2 potassium ions are usually transported during one pump action cycle. Through under artificial conditions, this relation can be another one. Sodium and potassium ions are transported across the membrane by the complex integral potential carrier that hydrolyzer ATP, whose energy activated the sodium and potassium pumps. This protein is known as the transported ATPase or potassium-sodium ATPase. Ion transport is caused by conformational change in the protein carrier. Ion transport during sodium-potassium pump action result in an essential difference in sodium and potassium concentration in and beyond the cell. One distinguishes cellular and extracellular concentration of some other ions, particularly chlorine ions. Such a difference in intercellular and extracellular concentration of ions with different charges yields a difference of potential between the outer and the inner surfaces of the plasma membrane. And biopotentials. In a state of rest, the cell's inner medium is charged negatively relative to its environment. The difference of potentials between the inner and the outer sides of a membrane is known as a membrane potential. If a cell is in a state of rest, the membrane potential is known as resting potential. The resting potential of different cells of various organisms can have different negative values in the range of about 50 100 millivolts. At present, the best model that describes the formation of the resting potential is a model which assumes that in the stationary state, the sum of flow of basic ions is equal to 0. And look at here, it's a conditional. Of the stationary state. Proceeding from this equation and using the Nernst-Planck equation, one obtains the Goldman-Hodgkin-Katz formula for the membrane resting potential. Look at here. Where phi r is the membrane resting potential. P P and A and P Cl is the membrane potential coefficient for potassium, sodium, and the chlorine ions respectively. This potassium plus in square brackets and sodium and chlorine are active concentration of potassium, sodium, and chlorine ions respectively. In this formula, the membrane permeability for an ion is considered as a proportionality factor between the density of flow of these ions across the membrane and the difference of concentration of these ions on both sides of the membrane. In the simplest model of ion diffusion across the membrane, the permeability of the membrane is equal to where K is the distribution factor of the particles of substance among the membrane and the environment. Lambda is the membrane thickness. The permeability of a cell membrane for different kinds of iron is essentially different. If one takes membrane permeability for potassium as a unit, then the following relation. Look at this relation. This relation shows the potassium ions have a key role in forming of the resting potential. The process of action potential formation is related to a significant and non-simultaneous change of membrane permeability for sodium and potassium ions. First, after reaching the threshold value, the sodium channel open and the bulk of sodium ions pour into the cell. This causes depolarization and subsequent membrane potential reversion. And look in this picture, and we can see these are depolarization. It's here. Then the potassium channel, and look at here. Then the potassium channel open and the sodium channel close. The bulk of potassium ions exit the cell. Then the potassium sodium pump activated to recover the sodium and the potassium concentration, which are close to the initial ones. As a result, the membrane potential again becomes negative. Membrane repolarization occurs. And the first phase, we can see three phases in this picture. And depolarization and repolarization and the first hyperpolarization. And first phase, a phase of depolarization, a change of polarity of membrane potential differences. And second phase, a phase of repolarization, reduction of amplitude potential of action, and restoration of polarity of membrane potential differences. And third phase, a phase of hyperpolarization, value of a module of membrane potential differences more than a stationary value of potential of rest. Duration, the form and the value of potential of action, essentially after for membranes of various cells. Action potential generation in a membranes section causes membrane potential changes in adjacent section of the membrane. If these changes exceed the threshold value, this in turn causes action potential generation in these adjacent sections. As a result, the action potential wave propagates across the membrane. In a muscle cell, the process causes its concentration. In the nerve cells, action potential wave propagation across the membrane represents nerve impulse transmission. And then talk about electric dipole and the physical basis of electrocardiography. Electric field is a talk about a basic characteristic of electric field. And electric field is a field generated by electric charges and performing the interaction. Electrostatic field is a field generated by fixed electric charges, the quantity of which does not change with the interval of time. Major characteristic of electric field. First, the first characteristic of electric field is called strength tension or intensity of electric field. It's a vector E. Look at here. It's a E. For one charge and for two charges with different sign and with the same sign. In some point of the electric field, the intensity is equal to the ratio of the force affecting from the electric field on a charge placed in this point to the value of this charge. And the first equation is E, electric field, this force, and this charge, Q, charge, is a test charge, a unit of a positive charge. F is the force acting from the direction of field on the test charge located at the given point. E is a vector physical quantity being the force characteristic of the electric field. And the dimension of strength or intensity of electric fields is a volt by meter. And then force lines. Force lines are lines tangents to which at each point of electric field coincides with the field vector at this point. Look at here. Force lines of electrostatic field are not closed. They start on the positive charges and finished on the negative charges or continue into infinity. Look at here. Into this situation and this situation. Second, the power characteristics of electric field are called potential. Potential differences, the delta phi. The potential of electric field is a scalar quantity being the power characteristic of the electric field. In some point, the potential of electric field is equal to the ratio of the potential energy of a charge placed in this point to the value of this charge. And potential differences or potential is equal to potential energy divided by test charge. And potential energy is dimension of strength is volts. The electrostatic field has a potential that is a Y work executed by a field equals dimension of potential energy. and look at here. It's a work. It's different of potential energy, and this test charge and potential difference. Where it's U is a potential difference. It's a difference of potential. It's a name also tension or voltage. It's a tension or a voltage. And potential difference is equal to work is a work done when in unit electric charges is move between 2 points having different electric potential. Geometric position of points having equal potential is called equipotential surfaces. And look at this picture. We demonstrate equipotential. It's these blue lines. It's equipotential surfaces. Look at here. For single positive charge, an electric dipole, and two equal positive charges. Correlation between characteristic of uniform field. The intensity is connected with the potential by the ratio. Look at here. Intensity of field is a gradient of potential. Is a different operator. It's a gradient. Is a different operator named gradient, and expressed through the partial derivative on coordinates. Gradient. We can write down gradient, use partial derivatives, where I, j, and k are the vectors of unit length or orth, directed along coordinate axes ox, oy, and oz accordingly. These components of the vector E along the specified coordinate axis are equal. Look at here. Ex is equal minus d phi divided by dx, and that's all. That we can write for intensity or E this form, and d is the distance along a direction E between points with a potential phi first and phi second. Sign minus in formula indicated that vectors is directed towards decrease of potential. The direction of the vectors of the potential gradient coincides with the direction of the fastest increase of the potential. Electric charges and the variable magnetic field generate the electric field. The intensity of the electric field created in some points by an isolated point charge Q is calculated by the formula. Look at here. E is equal, it's a model of charges, and divided by 4p epsilon epsilon 0 r in square, where epsilon is dielectric permittivity of medium, and epsilon 0 is electric constant, and r is a distance from the point in which the intensity of the field is determined up to the point in which there is a charge. At the same time, the potential of the field in the given point is calculated by the formula here. If the field is created by several charges, its characteristics are calculated from the principle of superposition of fields. According to the principle, the intensity of the electric field created in some point by several charges is equal to the vector sum of intensities of the fields created in this point by each of charges, and the potential is equal to the scalar sum of potential created by each of charges. Look at here. Where E and Phi are the resulting intensity and potential of the field created by charges. E first, second, etc., and Phi first, Phi second, and etc. Based on the principle of superposition of field, it's possible to calculate characteristic of the field created by various system of charges. Electric dipole is an aggregate of 2-point charges plus q and minus q of the opposite sign equal by quantity and placed at the small distance d from one another, which is called dipole arm. Look at this picture. It's a plus q and a minus, and this distance between these charges. The characteristic of dipole, electric dipole moment is a vector directed from the negative to positive, the p. With the amount that is equal to the produce of charge and the distance between them. It's a distance d. And the electric moment is a p, and we can write down these values. P is equal Q product with the D. D is the distance between these charges. The dipole generates electric field which differs from field of dot charges direction of the force lines. They begin on the positive charges and finished on the negative charges. And to talk about Einthoven's theory of leads. Current dipole or dipole electrical generator. In real condition, electric dipole cannot live long time. In electric field, the charges begin move and the dipole or will neutralized or will screened. And look this picture. As a current dipole can be a system in which electric potential different is remained, for example, part of electric current in which direct current present. On figure E, it's a voltage source, and R, equivalent of internal resistance of a voltage source. So R. Between points KK, current dipole is present. R is the equivalent of resistance of conducting medium, and R more or less than R small. Current in the circuit will be constant and will not depend on medium properties. Such dipole pole system consists of a spring and gutter of current placed on small distance d is named as a current dipole. Potential drop between two field points equidistance from current dipole is equal to delta phi is equal to p cos alpha divided by 4 pi epsilon 0 r square. In other words, potential drop between two field points equidistance from current dipole and electroconductive homogeneous medium is proportional to projection of dipole moment onto the straight line which connect these points. Electrography. All living tissue are source of electrical potential named as biopotentials. Electrography is a general name of all biopotential registering method that used with research and diagnostic purposes. Electroencephalography EEG is examination of electrical activity of brain. Electromyography is examinations of electrical activity of the muscles. Electrogastrography examination of electrical activity of digestive tract, first of all, stomach. Electrooculography is an examination of electrical activity of eyes, where oculomotor muscles are main source of signals. Most used method in everyday doctor's work is electrocardiography. The ECG records the electrical activity of the heart. This activity reflects the action of the cardiac muscles as it depolarized and repolarized during the cardiac cycle. The ECG represents the temporal and spatial summation of the action potential of the myocardial fibers, typically measured with body surface electrodes. ECGs are used to diagnose arrhythmias, abnormal electrolytes, potassium, calcium levels, and conductions abnormalities. They are also used for screening and therapy guidance for heart disease, as well as a cardiac gating for imaging. In order to get an electrical signal signal from the body, suitable electrodes amplification and appropriate display are required. Some cardiac cells generate action potential. One generated and under physiological conditions, and the action potential propagates through the cardiac muscles. The temporal and spatial summation of the monophasic action potential of the myocardial fibers produced an electrical signal known as ACG. Electrical activity of the heart. Look at here. The human body can be considered by purpose of an ECG large volume conductor. It's basically filled with a tissue surrounded by a conductive iron fluid. You can imagine that the heart is suspended inside of the conductive medium. During the cardiac cycle, the heart contracts in response to action potential moving along the chambers of the heart. As it moves, there will be one part of the cardiac tissue that is depolarized and another part that is at rest or polarized. This results in a charge separation or dipole, which is illustrated in the figure, this dipole. The dipole causes current flow in the surrounding body fluids between the end of the heart, resulting in a fluctuating electric field through the body. This is much like the electric field that would result, for example, if a common battery were suspended in a salt water solution or an electrical conductive medium. The opposite poles of the battery would cause current flow in the surrounding fluid, creating an electric field that could be detected by an electrode placed in the solution. A similar electrical field around the heart can be detected using electrodes attached to the skin. The intensity of the voltage detected depends on the orientation of the electrodes with respect to that of the dipole ends. The amplitude of the signal is proportional to the mass of tissue involved in creating that dipole at any given time. Using electrode on the surface of the skin to detect the voltage of this electrical field is what provides the electrocardiogram. Cells within the Sinoatrial node, it is here, are the primary Pacemaker site within the heart. These cells are characterized as having no true resting potential, but instead generate regular spontaneous action potentials. Unlike non-pacemaker action potential in the heart and most other cells that elicit action potential, the depolarizing current is a current primarily by relatively slow. There are in fact no fast potassium channels operating in Sinoatrial nodal cell. Potassium enters a node cell through opening channels. This results in slow action potential in terms of how rapid they depolarized. Therefore, this pacemaker action potential are sometimes referred to as a slow response action potential. Sinoatrial node action potential are divided into three phases. Phases is a spontaneous depolarization that triggers the action potential once the membrane potential reach their halt between minus 14 and minus 40 and minus 30 millivolts. Phase 1 is a depolarization phase of the action potential. This is followed by phase repolarization. It's a repolarization. Repolarization. It's here. When the cell is completely repolarization at about minus 60 millivolts. So look at here. So repolarization, and here threshold. The changes in membrane potential during the different phases are brought about by changes in the movement of ions. Movement ions across the membrane through ion channels that open and close at different times during the action potential. When a channel is open, there is an increased electrical conductance of specific ions through that ion channel. Closure of ions channels causes ion conductance to decrease. As ions flow through open channels, they generate electrical currents that change their membrane potential. And look at this picture. You can see William Einthoven was a Dutch physiologist who pioneered the ECG and won the Nobel Prize in Medicine in 1924 for this work. It was Dr. William Einthoven from the Netherlands who involved the EKG for clinical use by refining the electrometer and delineating PQRST waves. He used three lamp leads which become known as Einthoven triangle. Look at Einthoven triangle. Look at here. It's experimentally established that hot dipole during excitation generates action potential which on a surface of human skin gives the lines of equal potential. On the figure, positive of the dipole moment of a current dipole of hot and the equipotential lines is shown. If through a hot dipole to lead the straight line AB here, and through the center of arm of dipole perpendicular OO. Then on the part of positive pole of dipole heart settle down positive and on the part of negative lines of identical potential. The line OO have zero potential. Here zero potential. From the drawing is visible that if to apply electrode on various potential of surface of body of the person, it is possible to determine the potential difference of these points. For the first time, theoretical proved points on a surface of human body from which it's positive to take potential of heart have been offered by Einthoven. Dipole representation about heart underline the theory of leads of Einthoven. And we can see three leads, and first leads between two right and left arm, and the second leads from right arm and left leg, and the third lead from left arm and left leg. And the sign of potential, look at here, the minus minus and the plus plus and the minus plus. The main postulates of Einthoven's theory are the three main postulates. First, the electric field of the heart is represented as the electric field of the current dipole P, which is called the integral electric vector of heart. Second, P is inhomogeneous isotropic conducting medium that is a tissue of organism. And third, P permanently charges its direction and value. Look at here. And this the scheme of registration of ECG. And in screen or in paper, if we use electrocardiograph in the paper, we can see a typical ECG waveform for one cardiac cycle, measured from the leads to position. And it's look like this. And in laboratory work number 10, we use a cardiograph and we measure the ECG waveform and calculate it. Look at this waves, and the P wave denotes atrial depolarization. The QRS indicates ventricle depolarization, and T wave, look at the T wave, denotes ventricular repolarization. The event of the waveform occur on a scale of hundreds of milliseconds. And now want to you look a short to video about cardiac cycle and about a typical ECG waveform. Look at the screen. It's the first video.
The cardiac conduction system consists of the following components: the Sinoatrial node, or SA node, located in the right atrium near the entrance of the superior vena cava. This is the natural pacemaker of the heart. It initiates all heartbeat and determines heart rate. Electrical impulses from the SA node spread throughout both atria and stimulate them to contract. The Atrioventricular Node, or AV node, located on the other side of the right atrium near the AV valve. The AV node serves as electrical gateway to the ventricles. It delays the passage of electrical impulses to the ventricles. This delay is to ensure that the atria have ejected all the blood into the ventricles before the ventricles contract. The AV node receives signals from the SA node and passes them onto the atrioventricular bundle, AV bundle, or bundle of His. This bundle is then divided into right and left bundle branches, which conduct the impulses toward the apex of the heart. The signals are then passed onto Purkinje fibers, turning upward and spreading throughout the ventricular myocardium. Electrical activities of the heart can be recorded in the form of electrocardiogram, ECG, or EKG. An ECG is a composite recording of all the action potentials produced by the nodes and the cells of the myocardium. Each wave or segment of the ECG corresponds to a certain event of the cardiac electrical cycle. When the atria are full of blood, the SA node fires. Electrical signals spread throughout the atria and cause them to depolarize. This is represented by the P wave on the ECG. Atrial contraction, or atrial systole, starts about 100 milliseconds after the P wave begins. The PQ segment represents the time the signals travel from the SA node to the AV node. The QRS complex marks the firing of the AV node and represents ventricular depolarization. Q wave corresponds to depolarization of the interventricular septum. R wave is produced by depolarization of the main mass of the ventricles. S wave represents the last phase of ventricular depolarization at the base of the heart. Atrial repolarization also occurs during this time, but the signal is obscured by the large QRS complex. The ST segment reflects the plateau in the myocardial action potential. This is when the ventricles contract and pump blood. The T wave represents ventricular repolarization immediately before ventricular relaxation, or ventricular diastole. The cycle repeats itself with every heartbeat.
Second video.
The heart is essentially a muscle that contracts and pumps blood. It consists of specialized muscle cells called cardiac myocytes. The contraction of these cells is initiated by electrical impulses known as action potentials. Unlike skeletal muscles, which have to be stimulated by the nervous system, the heart generates its own electrical stimulation. In fact, a heart can keep on beating even when taken out of the body. The nervous system can make the heartbeats go faster or slower, but cannot generate them. The impulses start from a small group of myocytes called the pacemaker cells, which constitute the cardiac conduction system. These are modified myocytes that lose the ability to contract and become specialized for initiating and conducting action potentials. The SA node is the primary pacemaker of the heart. It initiates all heartbeats and controls heart rate. If the SA node is damaged, other parts of the conduction system may take over this role. The cells of the SA node fire spontaneously, generating action potentials that spread through the contractile myocytes of the atria. The myocytes are connected by gap junctions, which form channels that allow ions to flow from one cell to another. This enables electrical coupling of neighboring cells. An action potential in one cell triggers another action potential in its neighbor, and the signals propagate rapidly. The impulses reach the AV node, slow down a little to allow the atria to contract, then follow the conduction pathway and spread through the ventricular myocytes. Action potential generation and conduction are essential for all myocytes to act in synchrony. Pacemaker cells and contractile myocytes exhibit different forms of action potentials. Cells are polarized, meaning there is an electrical voltage across the cell membrane. In a resting cell, the membrane voltage, known as the resting membrane potential, is usually negative. This means the cell is more negative on the inside. At this resting state, there are concentration gradients of several ions across the cell membrane, more sodium and calcium outside the cell, and more potassium inside the cell. These gradients are maintained by several pumps that bring sodium and calcium out and potassium in. An action potential is essentially a brief reversal of electric polarity of the cell membrane and is produced by voltage-gated ion channels. These channels are passageways for ions in and out of the cell, and as their names suggest, are regulated by membrane voltage. They open at some values of membrane potential and close at others. When membrane voltage increases and becomes less negative, the cell is less polarized and is said to be depolarized. Reversely, when membrane potential becomes more negative, the cell is repolarized. For an action potential to be generated, the membrane voltage must depolarize to a critical value called the threshold. The pacemaker cells of the SA node spontaneously fire about 80 action potentials per minute, each of which sets off a heartbeat, resulting in an average heart rate of 80 beats per minute. Pacemaker cells do not have a true resting potential. The voltage starts at about -60 millivolts and spontaneously moves upward until it reaches the threshold of -40 millivolts. This is due to action of so-called funny currents, present only in pacemaker cells. Funny channels open when membrane voltage becomes lower than -40 millivolts and allow slow influx of sodium. The resulting depolarization is known as pacemaker potential. At threshold, calcium channels open, calcium ions flow into the cell, further depolarizing the membrane. This results in the rising phase of the action potential. At the peak of depolarization, potassium channels open, calcium channels inactivate, potassium ions leave the cell, and the voltage returns to -60 millivolts. This corresponds to the falling phase of the action potential. The original ionic gradients are restored thanks to several ionic pumps, and the cycle starts over. Electrical impulses from the SA node spread through the conduction system into the contractile myocytes. These myocytes have a different set of ion channels. In addition, their sarcoplasmic reticulum, the SR, stores a large amount of calcium. They also contain myofibrils. The contractile cells have a stable resting potential of -90 millivolts and depolarize only when stimulated, usually by a neighboring myocyte. When a cell is depolarized, it has more sodium and calcium inside the cell. These positive ions leak through the gap junctions to the adjacent cell and bring the membrane voltage of this cell up to the threshold of -70 millivolts. At threshold, fast sodium channels open, creating a rapid sodium influx and a sharp rise in voltage. This is the depolarizing phase. L-type or slow calcium channels also open at negative 40 millivolts, causing a slow but steady influx. As the action potential nears its peak, sodium channels close quickly, voltage-gated potassium channels open, and these result in a small decrease in membrane potential, known as early repolarization phase. The calcium channels, however, remain open, and the potassium efflux is eventually balanced by the calcium influx. This keeps the membrane potential relatively stable for about 200 milliseconds, resulting in the plateau phase, characteristic of cardiac action potential.